Well, good afternoon. It's 2:32. Sorry, I'm 2 minutes late getting started, but I had a stop to make on the way back to class after swapping off books, and it took longer than I anticipated. But nobody else is in the room, so we'll go on and get started from where we left off last time. I'll wait and make some announcements after everybody, or at least somebody gets here. And one of them is a very important announcement, so keep listening until you hear that announcement. If no one shows up, I'll try to make it the announcement at the end of class, but I wanted to wait until at least somebody was here to hear it. And then if other people come in, I'm going to be repeating it because it is that important of an announcement. So we'll go from current slide, and this is differential equations, Math 238. And we may have somebody here. Oh, it's Dr. Bryant. Yes.
I know you're looking for a student.
Yeah.
Yeah. Good question, please. Oh, yeah, one more thing.
All right, I'm back. Sorry about that. I thought a student was coming in. It turned out being Dr. Bryant, and he had a question for me. And then we got to talk about other things. And then when I started to record again, he came back with another thing he remembered. So now just getting back to it. So let's pick up where we left off before. We're in Chapter 4, which is Higher Order Differential Equations. 4.1 is Preliminary Theory Linear Equations. We're at the top of page 125. We had just been talking about the Wronskian, named after Joseph Maria Hoyne Wronski, okay, or something like that. It's called the Wronskian. Here are two functions, okay? The first of these, let me get my pen set up. Okay, sorry. First of these functions, y1 of x is cosine of 2 log x over x cubed. What a beautiful function that is. And the second of these is y2 of x, and this is sine of 2 log x over x cubed. Okay? These two functions. Now they tell us that these two functions are solutions of this differential equation. X squared y double prime plus 7x y prime plus 13y is equal to 0. Okay. On the interval 0 to infinity. Okay. Now, let me tell you why it's 0 to infinity. Notice that is the open parentheses in front of the 0. Notice right here, log x, log x. You cannot take the log of a negative number, and you cannot take the log of 0, ever, okay? So therefore, that's why you have to restrict this to positive values only. Not even 0, but anything beyond 0 will work, okay? Now, all right. I think the first thing we need to do is verify that both of these are solutions. So let's do y1 prime. Okay, I'm not going to put the of x. All right, quotient rule, and unfortunately not, well, actually, I think there is a better way around it. Let's write it like this. Cosine of 2 log x times x cubed, x to the minus 3, okay? Okay. I'm real tempted to put the x to the minus 3 in front, so I'm going to do that for this one. X to the minus 3 times the sine of 2 log x. Okay, the reason I like to write it in front, so you don't think it's part of the argument of sine, okay? That's one function, that's the other. Now, I prefer it this way because I prefer the product rule to the quotient rule. And with power functions, it's real easy to do this way. So, what is that? We'll do it the way I have it written here. The product rule says it's the first times the root of the second plus the second times the root of the first. So it really doesn't matter too much on this one. So let's do first, which is cosine of 2 log x times the derivative of the second, which is a minus 3 x to the minus 4. Okay? Plus the second times the derivative of the first. Well, the second is x to the minus 3 times the derivative of the first, which would be minus sine, so I'm going to change that minus to a plus, minus sine of 2 log x, okay, now we have to chain rule the second part. That's times 2 over x. Okay. That's your y1 prime. Now we can clean up a little bit. And what I'm going to do, I'm going to put the x to the minus 4th in front. Minus 3 x to the minus 4 cosine of 2 log x, okay, minus 2 x to the minus 4, because x to the minus 3 times 1 over x is x to the minus 4, sine of 2 log x. Okay, now to continue the cleaning process, that would be a minus 1 over x to the 4th. I'm going to put it, well, no I'm not. I was going to write it a little simpler, but since we have to take a second derivative, I'm not going to do that. Okay. Now, okay, like I say, we do have to take a second derivative, so let's do that next. y1 double prime is equal to first times the derivative of the second, that would be a minus 3 x to the minus 4th times derivative of the second, that's going to be a minus sine, so that's going to make that a plus sine of 2 log x, and then you've got a chain rule, and that's going to be 2 times 1 over x, so 2 over x. All right. Now, minus, wait, okay. Now, we have to do the second part of that, and because the whole thing was preceded by a minus, this is also a minus, minus the derivative of the first, which is going to be plus 12 x to the minus 5, derivative of the first times the second, cosine of 2 log x. Okay, my pen is really, really slow. Okay, that's the second derivative of the first term here. Let's do the second derivative of the second term, which will be minus 2x to the minus 4, that's the first, times the derivative of the second, which is cosine we're doing this one here, over there. Cosine 2 log x times derivative of the inside, which is 2 over x again. All right. That's the first times derivative of the second minus the second times derivative of the first. Well, derivative of the first is minus 4 times 2, which is minus 8. Yeah. But minus times minus is plus 8. This drives me nuts. Okay. Plus 8x to the minus 5. I'm waiting for the pen. Goodness gracious, this is such a pain in the neck. X to the minus 5 times the sine of 2 log x. All right. Now, when we combine these two together, notice that the 2 over x is going to make this a 4x to the minus 5. I'm just running out of room. So we've got everything times x to the minus 5, including this one. This will be 6x to the minus 5. Okay? And that. So I don't know where to write it. I think I'm going to write it up here. y1 double prime is equal to, and this time I think I will put it back in fractional type form. That would be 6 sine of 2 log x. No, I'm sorry. Yuck. You have a 6 here and an 8 here, so that's 14. So let's just combine these things. Okay. That'd be 14 sine 2 log x over x to the 5th. That's your two sine ones. And your cosine ones are a 12 here and a minus 4 there. So that's a plus 8. It'll be over x to the 5th. So cosine 2 log x over x to the 5th. So it does shorten and simplify a little bit here. Okay? So there's your y1 double prime. Okay? Now, let's simplify this one. I wasn't going to until now. This will be a minus 3 cosine 2 log x over x to the 4th, and a minus 2 sine 2 log x over, my pen is so slow, over x to the 4th. And it's not writing sometimes. There. Now it writes double. All right. Now, let's write our deal here. X squared times y1 double prime. Well, the x squared is going to bring this down to x cubed in the denominator. So we're going to have a 14 sine of 2 log x over x cubed. Okay, plus 8 cosine of 2 log x over x cubed. Okay, now we're going to do a plus 7 x times y prime. Well, here's our y prime over here. The x is going to bring that down to x to the third in the denominator. So that's going to be, I said a plus, but this is going to be a minus, isn't it? Because both of these are minuses there. So it's going to be a 7 times 3, so it's a minus 21 cosine 2 log x over x cubed, okay, minus, goodness gracious, this thing is so aggravating, okay, 7 times 2 is minus 6 sine 2 log x, sorry, over x cubed, okay? Then we got a plus 13y, where your y was, y1, was cosine 2 log x over 3, and you got plus 13 of that, so that's plus 26, I believe it is. Okay. All right, glad to see you. It's sort of boring talking to myself. Very boring talking to myself. I'm not a very good listener. Just got to get on the right page here. There we go. Pages from folding over on themselves. Okay. And down zero. All right. The screen has come up. I know you're so glad to see it. But before we do anything here, I told everybody I was talking with before, no one's here, that I would wait and do the announcements until somebody came here to hear them. Okay? So you're it. So here they go. I was going to say something about L Day, but it's already over with. Right.
Yeah, they still got the gates.
Yeah, and that's what Dr. Bryant came in to ask me what was going on while the gate was closed. So that's why in the first part of the class was a big dead period while we were talking, and then I came back on. But anyway, that's over with now. It may still be going on at Birmingham campus, but we can't get there in time before it's going to be over. It goes to 3. Okay, are you ever on the Birmingham campus?
Unless I'm working there now.
Okay. Just in case you ever are, if you're familiar with it, there's a Leon Kennedy Center was the student center. Okay. That building is now completely closed. Everything is moved into this new building, which is called the Academic Success Building. Okay. And you may have worked there putting in the lines there, I don't know. But anyway, everything there. The food services is there. As far as I know, the bookstore is there. The Space Center is there. As far as I know, even the police department moved over there. I don't know. They were in Leon Kennedy, and this email that they sent Monday said Leon Kennedy Student Center is closed. The cafeteria is now operating from the Academic Success Center. So I assume that means everything is out of Leon Kennedy over there. All right. Now, this was our administrative calendar, which most of it, to me, not very important. They didn't have L Day on it anyway. But there is something up that does affect this class, okay? And that is next Wednesday, 1 week from today, our wonderful chancellor's office down in Montgomery has said that all the faculty needs to come down for a professional development day. So I will not be on campus at all next Wednesday. I'll be here Monday, knock on wood, but I won't be on campus on Wednesday. I'll be in Montgomery all day. Now, I'm hoping to be able to leave early enough to get back for my 4:30 class on the Birmingham East campus. I doubt if I'll make it by 4:30, but hopefully the students will hang around and we'll get a class in. But if not, I'll just let them do the class that we recorded last time and we'll pick up from there. which is probably what we need to do unless you want to be in class, and then we'll just stop before we end Monday and pick up the following Monday. Is that what you prefer to do?
Yeah.
Okay, all right. So we'll do that then. But that's next Wednesday. Now, are you on campus at all on Thursdays? Okay. Well, Honors and Awards Day is next Thursday, not tomorrow, but the 11th. But that's in the morning, and that messes up classes in the morning too. So, but if you don't have any classes, that won't bother you. Okay, and then there's other things coming up later in the term. Okay, and then I think I told you last time about the NASA. Okay, so I won't repeat that. I did want to tell you I'm not going to be on campus next Wednesday. Maybe back for my evening class, but may not. We'll see. They say the meeting's supposed to end 3 to 3:15-ish, but then we still have to catch a shuttle from whatever building we're in to the sports, the stadium parking to get in a vehicle and drive back to Birmingham. And I don't know if I'm going to make it.
It's a 2-hour drive.
2-hour drive?
From Montgomery back to Birmingham.
Yeah. Okay. So Dr. Bryant said he thought about an hour and a half. And if I got to leave right at 3, I could be back by 4:30, but I don't think by the time I get the shuttle and everything else. Yeah, so you think it's more like 2. So 3 to 5. I'm not sure the students, well, they might. I'll tell them about it tonight, and if they want to meet next time, I'll say we'll just maybe wait. I'll leave it up to them. So appreciate you telling me that. All right. Now, what we're doing here is the top of page 125. They gave us these two functions. Y1 is cosine, one of your favorite functions here, cosine of 2 log x divided by x cubed. And Y2 is sine of 2 log x divided by x cubed. Okay? Now, first thing we had to do, of course, and then said, they just told us these are supposed to be solutions for this differential equation. Okay? This is the top of page 125, and you see these two equations written and then the differential equation. Okay? Now, what I said I was going to, and I also mentioned this, notice these are only good on the interval from 0 to infinity. Why there? Well, because of the logs there. Log is never defined for negative numbers or for 0. So therefore, that's open parentheses in front of the 0. Any other value will be fine. Okay. Now, what we have to do then is take that y1, and that's as far as I got, y1, and take a first derivative, and that's down here. Okay. Now now what I did, I rewrote both of those because I don't really like the quotient rule that much. I far prefer the product rule. So I rewrote, since the quotient was x cubed, I rewrote it as x to the minus 3, and then did it the product rule. Okay, so I did that for that one and that one. This one I forgot and wrote it at the end. I prefer writing it at the beginning so you don't confuse it, but it's the same thing. So then I took the first derivative by the product rule of that function there, the first times the derivative of the second, which introduces a negative 3 and an x to the minus 4, plus the first, the second times the derivative of the first, and the derivative of cosine is minus sine. Okay? And then you have a chain rule on top of it, your favorite, and the derivative of the chain rule would be 2 times the derivative of log x, which is 1 over x, and that's 2 over x. Okay. So there's the first derivative. Then I monkeyed around with it and did things with it. And I left it in product form here, but then later I changed there because it makes it easier for what we're going to do next. So with the product form, I took the second derivative, okay, which, and by the way, because when you take the derivative of the first one here, you get to x to the minus 4th. This is x to the minus 3, but when you take the derivative of the chain rule, by the chain rule, you get another x in the denominator. So that also is the x to the minus 4th, so 1 over x 4th. So both of those turn out that way. Then taking a second derivative, it goes to x to the minus 5th on both cases. Now, what I did was combine like terms here too. But anyway, that's the second derivative. Now, I cleaned that up by combining the two sine ones and the two cosine ones, and that's what I got for the second derivative. And I put it back in fractional form. Okay. So what I was doing next was plugging in the second derivative here. So x squared times this. Well, all the x squared does is reduce the x to the fifth to x to the third in the denominator. So it's that numerator, which is 14, plus that numerator, and these are both over x cubed. And then plus 7x times the first derivative of, and here's the first derivative in fractional form. And the x here wipes out the fifths in the denominator, I'm sorry, the fourth in the denominator, and get this to x cubed too. So then you have plus 7 times a minus 3, so it's minus 21, the cosine part, and then 7 times 2 is plus 14. Oh, no. I messed that. Okay. I'm glad I'm reviewing it. I'm all over the board here, so it's sort of, okay, let me do it again. We got a 14 from here, a plus 8 from there, 7 times 3, and that would be a minus 21 here, and this should be, I looked at the wrong thing, it should be a minus 14 there, and I already minus 6. So let me change that to a minus 14. Thanks for coming in. Okay. Okay. Minus 14. Okay. Now we have the plus 13 times y. Well, here's your y up here. Okay, so that's plus 13 cosine 2 log x over x cubed, which is very fortunate because everything has an x cubed in the denominator now. Okay, so let's see what we've got. 14 sine minus 14 sine, 0. Okay? 8 cosine minus 21 cosine plus 13 cosine. 8 and 13, 21 minus 21, 0. So sure enough, that comes up being 0. Now we can do the same thing for sine. Okay? Unless, but you see it's going to work out just about identical. So you're okay with it? Okay. All right. So we have shown that sure enough, at least the first one, and by extension the second one, is, I have confidence it's going to work out too, is going to be solutions for that differential equation. All right. So we've got that. The question now is whether they're independent solutions or not. And that's where the Wronskian comes into play, which we did near the bottom of the previous page. Okay? Now, before we go to the Wronskian, though, it says, now, what it says, suppose each of the functions f1, f2, f3, this is definition of the Wronskian, all right, I don't think that's what I need. Need the theorem 14.1.3, which is at the very bottom of the previous page. Let y1, y2, we only have two, be two solutions of the homogeneous. Okay, is this homogeneous? Yes, it's equal to 0. That means homogeneous. This equals 0 right here. Homogeneous or homogeneous, if you prefer saying it that. Linear, nth order differential equation. Oh, is this a linear nth order differential equation? just the differential equation. Notice the x squared, that doesn't mess up linearity, okay? 7x, that doesn't mess up linearity. 13, that doesn't mess up. What would mess up linearity is if you had a y times a y double prime, or a y prime times a y double prime, or a y squared, but all these are to the first power 1 each and every term, so that makes it linear. Okay, doesn't matter what the coefficient functions are. Okay, now if those are linear nth order differential equations, ours is second order. Okay, and we have two equations, so yeah, that works. On an interval I, we got it from 0 to infinity. Then the set of solutions is linear independent on I if and only if the Wronskian is not equal to 0. So that's what we've got to test next. Now I'm going to erase as much of this as I can, but I've got to leave some of it in place here. So I'm trying to get my eraser to work. We certainly need our original equations, and we certainly need the first and second derivatives. I don't think we need the differential equation anymore, but I could leave it. But what I don't need is this verification here that it's satisfied. So I'm going to take this out. And hopefully not get anything I don't need to take out. Oh, I lost my cube there because I'm writing too close together. Oh, I lost a 2 there. But we can lose the rest of that. Do I need that next line? I think I lost my prime too. So I'm going, but I don't think I need this one. All I need is that at the end. So I'm going to lose this. So all those things I lost there didn't matter, except the prime did matter. So I'll put that back. And this I don't think I need any longer. I'm going to hate it if I do, because I don't want to rewrite that, but I can get by with it. Okay. So your first derivative was this, okay? Y1 prime is that. Oh my word, I do need to take the derivative of the other one, otherwise I can't do the Wronskian. But I can write it down and it will just say we'll believe it.
We can take the derivative, but that means we have to verify that it's
Right, okay, yeah, but that was the hardest part. But anyway, so I've already got the second derivative up there. Oh, let me get my eraser back. Okay. Even cheaper than what you said, I'll just write down what they told us the derivative is and second derivative. Okay. Okay. Would you like to take the derivative of it?
Yeah.
Okay, let's do it. Then what I'm going to do is rewrite my y prime up here, just so it'll be more convenient space-wise. Y1 prime of x.
Oh yeah, we're doing Y1.
Yeah, we're going to do y2, so I'm just writing y1 up here, is equal to minus 3 cosine 2 log x over x to the fourth minus 2 sine 2 log x over x to the fourth. This is such a pain in the neck. Okay, so now I'll erase this one. Okay. Well, I said I would erase it. The eraser is slow. Okay, so let's do the second one, y2. So we're going to do y2 prime. Okay. All right. here's our y2 written there. So y2 prime is going to be the first times the derivative of the second, right? So that's going to be x to the minus 3 times the derivative of sine, which is cosine, 2 log x. That's pretty ugly writing up there, but log x. But then I've got to do chain rule, and that's going to be another 2 over x. Right? Okay. That's the first part, okay? Plus the second part, which is going to turn out being a minus, I know, is derivative of the first. That's where the minus comes in. 3x to the minus 4, right, times the second, sine of 2 log x. Okay. Now, because I did it last time, I'm going to do it this time too. I'm going to rewrite that ever so slightly to get this coefficient out in front there. So that's going to be 2 cosine 2 log x. I can't see because it's writing so slowly. And that's why the writing gets so sloppy, because I can't see what I'm writing. That's a log x there, over the 2 is from here, and this is x cubed plus 1 more is x to the 4th. Okay, minus 3 sine 2 log x over x 4th. Okay. Now, doing the second derivative, y2 double prime, I'm going to use these forms because these are easier to deal with. Okay. But I'm going to bring this 2 over here and make this x to the minus 4. Okay. And get rid of that one. Okay. I'm going to do the same thing here. No, that's already minus 3x4. Okay. All right. So, taking the derivative of this thing first, which is 2x to the minus 4 times the derivative of the second, which is a minus sine of 2 log x. But then we have the chain rule, which puts another 2 over x, right? Okay. Plus, which is also going to turn out being a minus 2, the derivative of the second, derivative of the first times the second, and that will be, the derivative here is going to be a minus 8 x to the minus 5 times the cosine of 2 log x. Okay, that's the...
Why is that a negative?
Because...
You're multiplying negative 2 by 2.
Okay, yeah. Here's the y prime.
You're right.
So minus 8, yeah, the derivative of the first is minus 8 x to the minus 5 times this.
I was looking at the one right below it. It's negative 2, negative.
Right. Oh, this one?
Yeah, that's what I was looking at.
Okay, yeah, okay. Now that one, negative, because you wrote down the first one, 2x to the minus, no, we didn't. Yeah. 2x to the minus 4, and it's negative because the derivative of cosine is minus something. So that's why that minus showed up there with that times that. Okay. So, now, that's just the first one. We've got to do the second term now, derivative of the second term, which I'm going to put the minus there. The first, 3x to the minus 4 times the root of the second, which is going to be cosine of 2 log x times the derivative of 2 log x, which is 2 over x. Okay? And this one's going to turn out being a plus, because the derivative of the first is going to be minus 4 times minus 3 is plus 12. x to the minus 5 times the second, which is sine of 2 log x. And again, that's an ugly log. Okay, I don't know why it's not writing well. Okay. Now we're going to simplify this a little bit by combining this 2 over x here and making that a minus 4 over x to the minus 5. You okay with that? The 2 times 2 is minus 4, and this will be x to the minus 5. The only reason I'm doing it this way, I just don't have any room to write. Okay. And here this will be, that's okay. This one, I'm going to combine this 2 over x and make that a minus 6 times x to the minus 5. Okay, and that one's okay. So if I combine the sines and cosines together here, this gives me, the sines are a minus 4 and a plus 12, so that's going to be 8 sine 2 log x over x to the 5th. And this one would be minus 8 minus, so that's minus 14 cosine of 2 log x over x to the minus 5. Hopefully it'll show up and turn off. Okay. All right, so that's how those simplify.
You got negative 5 in the denominator.
Oh, yeah, you're right. There's a plus. Okay. Keep them erasing. Okay. Now we do the Wronskian. Thank goodness it's only a 2 by 2. Okay. So what is the Wronskian of these two functions? The Wronskian of f1 and f2. Okay. It's the determinant of a 2 by 2, and it's the function on the top line and the first derivative is on the bottom line. So I really didn't need that second derivative. Sorry about that.
Well, according to the definition over here, wouldn't you need?
What's that?
On the other page.
Yeah.
Right there.
Right.
Wouldn't you need the second derivative?
No, okay. Notice here, the Wronskian of the functions, however many you have, we only have 2. Then you would do the function first derivative down to the n minus first derivative. We only have 2 derivatives, second derivative, so we only go into the first derivative. So we get a 2 by 2. Your size of your determinant is the same dimension as your order of your differential equation. And it's the second order differential equation, so we're 2 by 2. We don't need the second derivative there. If this had been, if we'd had a third equation, then we'd need the second derivative, but we wouldn't need the second derivative, we wouldn't need the third derivative. Okay. All right. So this Wronskian will be these two functions, which is cosine of 2 log x over x cubed, sine of 2 log x over x cubed. That's the top line. The second line is this expression. And unfortunately, here's the y1, and here's the y2. Okay. I'm going to have a hard time writing that in that little space. But I put the y1 first, which is minus 3. Okay, what I think I'm going to do is put it all over the same x4th denominator. Okay. It's not going to save a lot, but a little bit. Minus 3 cosine 2 log x minus 2 sine of 2 log x over x fourth. Okay? I'm going to do the same thing for the first derivative of this one, which is in that next block, which is 2 cosine 2 log x, yuck, minus 3 sine of 2 log x. If you can read that, you're amazing. Okay? And that's all over x to the fourth. And then somewhere out here we have the end thing of our...
Now, here in the book, they've got x squared in their signs, in their first derivatives. They've got negative 3x squared cosine.
And they did the quotient rule, which did that to them. But if you'll notice there, in their numerator and denominator, in their numerators, they have an x squared term in both of the ones for the first and in both the ones for the second. If you factored that out, it would wind up with x fourths in the denominator, and you would have, I think, exactly the same thing that we have. Okay? Yeah, believe that's right. And they reverse the sine and cosine orders, but that doesn't really matter. Well, they did on the first, but not on the second. I don't know why, but yeah, that's what they did. Okay. Oh, I know, because I did them strangely. That's my fault. All right, so what the Wronskian does, what a determinant does, is the product of these two minus the product of those two. That's what a determinant does. The product of the main diagonal minus the product of the other diagonal, the upward. The downward diagonal is positive, the upward diagonal is negative. So let's just take a look at this and see what.
One more time, say that again. The
Okay.
diagonal down.
The downward diagonal is the positive product, and the upward diagonal is the negative product. Okay. So it's minus the product of that. So let's see what that produces for us. Okay?
Right.
For the cosine, we're going to have 2 cosine squared 2 log x minus 3 cosine 2 log x sine 2 log x, okay, over x to the 7th. Okay? So let me write that down. Hey. So this one times that one, that's the first one. This will be 2 cosine squared 2 log x minus 3 cosine 2 log x sine 2 log x. Really getting, and all that is over x to the 7th. Minus the upper diagonal. Okay? This is going to be, and it's a minus, but you have a minus here, so that's going to be a plus 3 cosine 2 log x sine times sine of 2 log x, okay, plus again 2 sine squared of 2 log x. And that's going to be over x to the 7th. Okay. Now let's see what we've got here. 2 cosine squared plus 2 sine squared of the same thing. That's going to be 2. Right? 2 cosine squared of that and plus 2 sine squared of that. Factor out the 2's, cosine squared plus sine squared. Whatever the argument, as long as they're the same arguments, and they are, 2 log x, that's going to be 1. So that's 2 times 1 is
Sure is, okay.
okay.
I'm sitting here, I had to go back to trigonometry
Right.
for that.
Yeah. Okay. So that's the first one. Okay. And then you have a minus 3 cosine 2 log x sine 2 log x plus 3 cosine 2 log x. Those add to 0. But This is 1 over x to the 7th. And guess what, folks? X, that's never equal to 0, ever, okay? Because x is always positive, so whatever positive number you got there, it's never going to be 0. Now, sure, as you go, x going to infinity, it's get closer and closer to 0, but it's never 0, okay? So that's all the Wronskian is asking. Is it 0 or not? It's not 0, so therefore these are linearly independent. That's it. Okay. Huh? Oh, they. Oh, I said 2 and I wrote 1. Okay.
One heck of a test.
Yeah. Yeah. Now, then they tell us, rather than expanding this unwieldy determinant, we choose x equal 1 in the interval 0 to infinity and find that the Wronskian of y1 of 1 and y2 of 1, and by choosing x equal 1, okay, yeah, the log of 1, okay, the only place x shows up here is in the power and in the log. Log of 1 is 0, isn't it? Yeah, log of 1 is 0. So that would be cosine of 0 is 1, so it's 1 over 1, okay? And cosine and sine of 0 is 0, so that doesn't give you anything. So you turn out with 1 plus 1 is 2. There you have, I mean, it's there. The fact that the Wronskian there is sufficient to conclude that it's linearly independent. I can't quite justify that, but they say it is, so I'll take their word for it. It wasn't hard to do this way. It was just messy to write, but it wasn't that hard. But they just chose one value, selectively 1, and that gives you the log of 1 is 0. And then cosine of 0 is 1, sine of 0 is 0, so that made everything a lot easier. And you see, if you chose that, cosine of 0 is 1, and 1 over 1 is 1. Sine of 0 is 0, 0 over 1 is 0, and that's where they got the first part. This one, cosine of, the log of 1 is 0, cosine of 0 is 1, so that's minus 3. Sine of that is 0, so it's minus 3 over 1, which is minus 3. That's how they got the second, first entry there. And this one would be 2 minus 0 over 1. So that's where they got the 2. Oh. So it was pretty easy to come up with that. Yeah, that would have been 1, 0, minus 3, 2. The cosine ones are the only ones that come up with anything. And the denominators are all 1s. And then when you do that Wronskian, you still get 2 minus 0, which is 2. I mean, that determinant. Product here minus the product there is 0. So, now, I guess what they're saying, what we showed before, it came out being non-zero, and that meant non-zero everywhere, so if it shows up non-zero anywhere, it must be non-zero everywhere, though I can't justify that, but they say it's true. All right. Theorem, how are we doing on time?
Oh, we got 5 minutes.
5 minutes, good. Theorem 4.1.4. I think I'm going to go to a clean page, get rid of this. The main reason I did this was that seemed to be taking the derivatives and chain rule and things like that. I thought sounded like a thing that would be good to review. So were you okay with that?
Yeah.
Okay, good. All right. Theorem 4. Definition 4.1.3. Any set, and you got your book, so I'm not going to write this. Any set, y1, y2, up to yn of len in linearly independent solutions of a homogeneous nth order differential equation on some interval I is said to be the fundamental set of solutions for the interval. There's a definition. Fundamental set of solutions. If you have these, now in this one they just told us what they were. Later we're going to be determining them for ourselves. Okay? That'll be, I like it better than doing this, but just having to take the word for it. Okay? Then the next theorem, 4.1.4, the existence of a fundamental set, there exists a fundamental set of solutions for the homogeneous, or homogeneous if you want to call it that way, linear nth order differential equation on interval I. This just says there exists a fundamental set of solutions for the homogeneous linear nth order differential equation on interval I. They just tell you that it does. Okay?
Kind of like saying redundant.
Yeah, kind of. Okay. Then on the next page, the next theorem, 4.1.5. The general solution. Okay? Let's those same y1, y2 up to yn be a fundamental set of solutions for the homogeneous or homogeneous linear nth order differential equation on the interval I. Then the general solution, okay, not the fundamental solution set, but the general solution on the equation is y is equal to c1y1 plus c2y2 plus c3y3 plus c4 up to cnyn, where ci's are arbitrary constants. Okay, and if they're linearly independent, that means not all of those constants could be zero. There's at least one that's not zero. Okay. So, theorem 4.1.1 says there is a set of solutions. Okay? There exists some fundamental set of solutions. Okay? And there will be n of them if it's an nth order differential equation. Okay? There are those n solutions. Okay? This one said the general solution will then be some linear combination of those n solutions. Okay? And that's where you put your C1, C2, and C3. In the previous chapter that we did with first order differential equations, we usually only had one C because there was only one first order differential equation. When we had two, then there were two C's. This says there will be a C for each one. Okay? Doesn't specify what they, but only says they can't all be zero. Okay? And they prove it here for n equal 2. I'm really not all that anxious to do the proof. Do we have time to do example 7?
We got like 1 minute.
1 minute. I don't think so. So we'll pick up with example 7 next time. Sorry we didn't get much done today. You weren't here to hear it, but I came in. I was only like a minute or two late because I was trying to find out about that meeting next Wednesday. So just about to get started with the teaching when Dr. Bryant came in to ask me why the gates were closed. Okay, so we went over all day and that kind of stuff. And then he had gotten going. I just had started the recorder again, and he came back to, oh, by the way, about the other thing we're talking about. Since he didn't have but one student in there and I had none, he thought, let's clear out some of this administrative stuff. So we talked about another issue. So that's why we didn't get much covered today. But anyway, we'll pick up with example 7 next time. Homework exercises here would include, and this is repeating several, either 1 or 3, if they're in the back of the book, any of the odds 5 or 7, if they're in the back of the book, 9 if it's in the back of the book, 11 if it's in the back of the book, 13 if it's in the back of the book, and we're in 4.1.2 now, yeah. Any of the odds 15 to 21 if they're in the back of the book, and I think we can hold off on 23 to 29 until we do the rest of those. Okay? All right. Good deal. All right. And we'll pick up and go from there on Monday. I will not be here on Wednesday of next week, but I will be here Monday. Knock on wood, I'll be here Monday.